So today I want to talk about our recent project that was funded by USDA on the impact of zinc speciations on uptake of PFAS in alfalfa. So we are located in El Paso. I don't know if you have a chance to visit El Paso. It's far west in Texas, maybe far west in the United States. It's in borderland. Very interesting area because it's a cross section between a state of Chihuahua in Mexico, state of New Mexico, and Texas. So we have a strong cultural heritage beyond Mexico. Very interesting city surrounded by mountain. However, geographically we are pretty remote. So we are located in El Paso. If you get a chance to visit, hit me up, we can meet up, and I will give you a tour of El Paso. So many of you have heard about PFAS. What is really PFAS? A long chain or short chain of carbon. This carbon polymer has been shielded with fluorine. So this is a strong bond between fluorine and carbon. Nothing can break this bond. Not even microbial community, not even extreme heat. That makes it very commercially beneficial for us because it has a lot of applications. When we talk that nothing can break this bond, not extreme heat, so you can see a lot of commercial benefits. Everything around us, me and you, we have something in common, that's PFAS. Either it's in our blood or in clothes, because many things has some percentage of the PFAS in their formulations. That's why their application is very diverse. Tracking and the forensics of PFAS fate in agriculture, in environment is very, very complex because we are dealing with very complex chemicals. So they are short chain to long chain. So the production line of long chain has been ceased. However, they replace it with short chain PFAS. But it's solved a problem? No, because they use higher quantity of short chain PFAS to have the same function. But short chain PFAS, they have higher mobility. That makes it very complex. So if you look at the structure of PFAS here, we have one polar head. That's like a head of the worm that drives its actions based on the polarity, surface charge. And also we have some lipophilic and hydrophobic chain that also drives their attachment to the environment. So their fate and effects to the environment, to the existing mineral, is very, very complex to understand. So when we talk about this is resistant to extreme heat, one main application comes in mind. What is that? Firefighting foams. It has been main ingredients of firefighting foam. Imagine in US, we have how many military bases? Even outside US. All of them, they go through regular firefighting training practices. And we are expected to release high quantity of PFAS to the environment. Either they go directly to the soil or water or atmosphere, but all of them, they find their way to agricultural soil and contaminate our crops. So when they end up in vadose zone or agricultural soil, also the type of PFAS is very complex to drive the speciation of different minerals or even their uptake. Because some of them, they are soluble, some of them less soluble, and also the plants, they behave differently. We have perennial plants with short root lengths or trees with long root lengths. All of them will impact their uptake in the shoot area or canopy of the plants. So their toxicity will be very complex based on the plants, based on soil properties, and also the physiochemical structure of PFAS are also very, very diverse because we have PFAS with positive surface charge, negative surface charge. We all know that root epidermis have negative surface charge, may absorb PFAS with positive surface charge, or short chain or more soluble PFAS, they can drain all the way to the groundwater system. So their uptake have been very complex, and many things can impact their bioaccumulations in the plants. So we already know microbial community, type of species, non-aqueous liquid phase, water, air in the soil compartment can impact their fate and their speciations of different minerals in exposure to PFAS. However, nanoparticles have come in the picture, at least in this study, and recently they have used high quantity of nanoparticles because they are using it as a stimulator for plant growth. Some of them intentionally as a stimulator, some of them unintentionally as a pollution. They end up in soil. In this study, we use zinc oxide nanoparticle. Why we use zinc oxide nanoparticle? Because it's one of the FDA approved nanomaterial for plant growth in the environment. So they have been approved by FDA. So we have a standard for many contaminants, pesticides, heavy metals, but we do not have really a standard for PFAS. It's very complex because it's not one or two. Even US EPA have regulated only 6 types of PFAS, not all the type of PFAS. And we don't have even a standard for PFAS, all PFAS. So it's very complex. Also, we are in the beginning of way to characterize the PFAS contamination and see what we are dealing with and what we can do with different type of PFAS that they have higher importance in our economy, in agriculture. So, for example, you can see the rice paddy soil. The PFAS can go through irrigation as a mistreatment or as biosolid. Imagine how much biosolid we can produce it. Here you can see the wastewater have been characterized based on concentrations of the PFAS. We have domestic with less concentrations of the PFAS, all the way to intensive concentrations of the PFAS in industrial wastewater. All of them resulting to generations of biosolids. Biosolids is one of the now one of the main application or primary application is soil amendment. So we are expected to have so many contaminations of crops by applying biosolids. Over 50% of biosolid produced in US using soil amendment, and also over 40% in Europe they are using as soil amendment. So imagine how much PFAS we are just consuming in our salad, and we are not aware of that. So it's very interesting that we investigate and see the way and how we can provide a safeguard for our crops. So in the big picture, if you imagine like a hydroponic system or just a soil system, we have presence of the PFAS and nanomaterial. Many things can shape the transformations of the PFAS or speciations of nanoparticles. So we are dealing with zinc oxide nanoparticle. Zinc oxide nanoparticle, they have antimicrobial properties. So it means that it can reduce the amount of microbial community. However, soil also as defense mechanism, they release root exudate as a defense mechanism. Root exudate will reduce the pH. We are expecting to have more dissociations of zinc oxide nanoparticle to ionic form. So we don't know if this ionic form will chelate or form some sort of ligand with PFAS. Do they increase the uptake of PFAS or reduce the uptake of PFAS? What about soil retention? So these are all the questions that we have to answer based on what we are expecting in soil microenvironment. So what we can expect regarding the PFAS uptake or soil retention, then how we can monitor and safeguard